So today we're going to be talking about trees. So we know that there's a lot of different types of trees. We have the oak tree and the maple tree.
Joking.
Yeah.
We're not talking about actual trees. We're talking about trees in the context of data structures and algorithms. So, yeah. Let's just talk about what a tree is. So a tree or trees, they are data structures. So what that means is that we can use trees to store data. So whether it be numbers, letters, etc. They're a way of storing data, just like linked lists and things such as that. So with trees, they have two main things. They have edges and they have nodes. Okay, so nodes are the things that actually hold the data, and we typically represent them as like a box. And these nodes, they're connected to other nodes via something called edges. So they're just like the lines connecting the nodes together. So if we're to visualize that, here are some example trees. So your tree could be something like this. So this is called the root node, and these are child nodes of the root node. So in this case, you can have like 3 branching from it, or you can have like another tree that's like this, where everything is just to the left of the previous node. So there are different ways to visualize trees, but one particular version looks like this. So this here is what we call a binary tree. So it's called binary because you can only have 2 nodes under each node. So binary, if you recall from 192, like, you can only have zeros or ones, right?
So with binary trees, there are different ways that we can go through the tree. So these are called traversals. So the first traversal is called a breadth-first traversal. So what that means is that we're going to go through each node at each level of our tree. So we have 1, 2, 3, 4, 5, 6, 7. And that's the order of the nodes that we'll visit. And that's our output for a breadth-first traversal. Now we just saw the breadth-first traversal. Now there's something called the depth-first traversal. So instead of going level by level in breadth-first, we're trying to go from the bottom up. So in this case, bottom would be node 4, and then up would be node 1. So there are 3 different ways to approach our depth-first. So the first one is called in order. So for the in order traversal, what we're trying to do is we're trying to visit the left subnode first. So first we start at 4, then we go up to the root 2, and we go visit the right, which is 5. And we go upward to 1, and then 6, 3, and then 7. So that's our order for in order. So the second traversal is the pre-order traversal. So what that means is we're going to visit the roots, then the left, then the right. So in this case, we're going to start at the root, which is 1, go to the left 2, and then left again 4, and then 5, and then 3, 6, and then 7. So that's our order for pre-order. So finally, we have our last traversal, and that is called the post-order traversal. So the idea is that we're going to visit the left, and then the right, and then the roots. So in this case, we're going to visit the leftmost, which is 4, and then the right 5, and then the root 2, and then the leftmost of the right branch 6, the rightmost of the right branch 7, and then the root 3, and then finally our final node 1. So that's our order for post-order traversal. Okay, now on to binary search trees. So binary search trees is just a binary tree, but there's a specific structure to it where if we want to add something, it can only go to the left or right of it, right? But we have a rule for what can go to the left and to the right nodes. So for example, if we were to insert 8 as our root node, our first node, and then we want to insert something like 3 is less than 8. So what that means is that it has to go on the left. And then if we insert 10 has to go on the right because it's greater than 8. And that's just the rule that you have to follow for binary search trees. If it's less than the current node, then we go left. If it's greater than, then we go right. So now, continuing this trend on, if we want to insert the number 1, well, we will have to go down our tree again. So what that means is that we're going to start at our root node, which is 8, less than 8, less than 3, and that means we put it at the left of 3. Now, let's say we want to insert another value, 6. 6, well, obviously it's going to be greater than 3, so that means it's going to be on the left, the right of 3. And then let's say we want to insert another value, like say 14. We know that 14 is greater than 8, so it goes right, and then greater than 10, which means it goes right again. So that's how we build our binary search trees. Now let's talk about the deletion of values in a binary search tree. So as you can see, this is a binary search tree because it follows the rule where everything less than our node on top is to the left, and everything greater than it is to the right of it. So in this case, we have a binary search tree that has different cases of removal. So for example, if we want to remove node 85 over here, this is called a leaf node because there's nothing, like there's no child underneath it, there's no node underneath it. So what that means is that if we were to remove it, we can simply just remove it, just like that, and there wouldn't be a problem. Now let's talk about our second case. So let's say we want to remove 115 over here. So 115, well, we can remove it, but there's a child node underneath it. So what that means is that when we remove it, we're going to have to just bring up our child node because it's only 1, right? So that means we can just bring our 120 on top over here where it previously was. Okay, now we have our final case, which is like in the case where we want to remove node 150 over here. So 150 is tricky because there are multiple like child nodes directly under 150, right? There's 135 and 175, and underneath those, like there are even more like child nodes, right? So what that means is that we're gonna have to replace 150 with one of the leaf nodes down here. So you have two options. One is called the predecessor. So what that means is that we're going to look at the left branch of 150, and we're going to find the value that is the largest in the left subbranch. So that means it's the rightmost element in the left subbranch, which is 136 in this case. So that is our predecessor. So we can use 136 to replace 150 over here. Or our second option is to use the successor. So the successor, we go to the right subbranch, but we want to find the leftmost element, which in this case, it would be 170. So we could use either one of these values to replace 150 up here. So if I were to use the predecessor, I remove 150 and then get rid of 136 down here. And then I just bring 136 up here. So that's what a removal would look like if there were more than one child node. In the other case where we use the successor, it's the exact same procedure. We just bring the successor up here, and then we move the successor 170. Now, the final type of tree that we're going to talk about is a self-balancing tree. So what that means is that these trees, they have a balance to them. So what that means is that essentially there's like one rule, and in this course the rule is that the balance factor is the height of the left branch subtracted by the right branch. So in the case of AVL trees, balance is maintained by ensuring that your balance factors never exceed 1. Okay, so we can draw out the balance factors for each node inside of this tree. So for example, if we had node number 9 over here, right, we would subtract the left tree and the right tree of 9, like the height of them. But in this case, since 9 is a leaf node, the balance factor is 0. Okay,
Now, in the case of 8, 8 has nothing to the left of it, so that's 0, but we have one thing to the right of it. So this one has a balance factor of -1. 11 over here, well, it has 2 items to the left of it, but we have nothing to the right of it. So this one has a balance factor of 2. 21 over here, nothing to the left, nothing to the right, so this one has a balance factor of 0. 13 over here, we have 3 items on the left branch, and we have 1 item to the right, so 3 minus 1, we have 2 as the factor over here again. 61, nothing, so that has a factor of 0. 53, nothing to the left, but something to the right, so balance factor of -1. And then for the top, well, what's the height of the left branch, right? What's the longest path? So we have 1, 2, 3, 4. We have a height of 4. And then on the right side, we have a height of 2, right? So what that means, 4 minus 2, we have a balance factor of 2 for the root node as well. So there are 3 areas where this AVL tree is imbalanced because they break the rule of having a balance factor less than or equal to 1. So to fix this, there are things that you can do called rotations, which we'll dive into next. So here's our first rotation. It's the left rotation. So what that means is we have a tree that looks something like this. And if we draw the balance factors for each of the nodes, we'll see that there's like a negative, meaning that the right branch is larger than the left branch, right? Obviously, there's nothing on the left branch over here. So we have a balance factor of -2 over here. So what that means is we have to do a left rotation about node 10. So what we're going to do is we're going to rotate node 10 to the left, meaning it takes the place of 5, making it the root, and the root node 5 is brought down. So ultimately, we're going to end up with something like this. And that's going to be our left rotation. Our second rotation is the right rotation. So now we have something that kind of looks like the opposite. We have 3 nodes once again, but this time we have a positive balance factor, meaning that the left branch is larger than the right. And since it's imbalanced at node 10 over here again, we're going to do a right rotation. We'll bring up node 5 to 10 and node 10 downward. So we're going to end up something like this. And that's going to be our right rotation, and now it's balanced. Now the next rotation is the left-right rotation. So this one's like a little trickier, but here, like, once again, we have 3 nodes, and we have a balance factor of 2 on this side. So meaning that the left is heavier here. So if we do a left rotation about 0.7 over here, we can bring it up. And then now it's still imbalanced, but if we do a right rotation, then it's balanced. So we rotated node number 7 left, and then finally we rotated node number 7 right, bringing it up to the head. So that's our left-right rotation. And then finally we have the right-left rotation. So kind of similar, it just looks like the opposite of the left-right rotation. So we have something that is right heavy because it's -2 over here. So if we do a right rotation about node number 12, like we bring node number 12 to the right up, and then node number 15 down, we still have something that's imbalanced. But if we rotate it one more time to the left about 0.12, then now it's perfectly balanced. So now we're going to go over an example of deleting a value from an AVL tree. So it's pretty much the same as if I were to delete a value in a binary search tree. So we have the predecessor and the successor. So let's say I want to get rid of 25 over here. So I can choose the predecessor, which is the largest value in the left subtree over here, or I can use the successor, which is the smallest value in the right. So in this case, it's probably easiest if I just used a successor because it's just one node over here, right? So pretty much all I'm gonna do is I'm just gonna get rid of 25 over here and 26 over here, and I just bring 26 up to where 25 was before, and now I deleted the value 25. But now we have to check our balance factors every time we do an operation like adding a new node or deleting a new node. So in this case, I'm going to mark the balance factors in this blue over here. So 0, 1, 2. This over here has height of 3. Right has a height of 4. So balance factor of 1 over here. Balance factor of 1, minus 1, 0, 1, 1, 0, 0. So in this case, we just have one node over here where it's imbalanced. So all we have to do to fix this, we can see that's left heavy. We can just do one single right rotation from node 10, and it would pretty much fix this imbalance that we had. So what we're going to do is we're going to bring node 26 down. Oops. And then we're just going to link up 10 to 50 where... Alright, now we're going to check the balance factor of everything else again. So in this case now, height over here is 2, but height on the right side is 4. So what that means is that our balance factor at the topmost node over here is actually going to become 2. So now we have another imbalance. Or rather, it's minus 2, because the right subtree is larger than our left. So we're going to observe our tree over here, and we're going to look for a pattern. So we have a minus 2 over here, and then we have a 1 over here. And we notice that, if we were to trace the chain of like the height or like the longest chain in the right subbranch, we see that there's this zigzag pattern. And that's a sign that we probably have to do either a right-left or a left-right rotation. So in this case, since we are right heavy at node 50, and then we have a long chain of on the left directly to the right of 50, what we're going to do is we're going to do a right left rotation. So we're going to rotate this subtree right, and then once we rotate this subtree over here, then we can rotate the entire thing left to balance out everything else. So what that is probably going to look like is we're going to rotate node number 55 over here to the right. So rotate node 55 to the right. How we're going to do that is we're going to bring 55 up, and then we're going to keep 54 over here on the left side, the same place it was before, but this right branch over here has to be brought down to the right of 55. So we're just gonna select everything here, and we're gonna move it down, and then we're gonna select everything here, and we're gonna move it up. Ignore the balance factors for now. This 56 over here, we actually have to just put that to the side for now, and then we'll move our node number 60 over here, and then we're going to connect it. Okay, and now with this node 56 over here, we can just add it as if we were just inserting 56 into our tree. So we're going to be at node 55. 56 is larger than 55, so we're going to go to the right. And it's less than 60, so that means we're going to put 56 over here. So right now, if we recalculate the balance factors for everything again in this right subtree, would see that node number 60 has a balance factor of -1 now, and 55 has a balance factor of -1 as well. Height is still 4 on the right subtree of 50, and height is still 2 on the left side. So it's still, we still have a balance factor of -2 at node 50. But now is the left rotation part now. So what we're going to do is we're going to rotate node 55 over here to the left, then bring node 50 down to the left of 55 and keep node 60 to the right. So instead of just shifting everything around, I'm just going to retry it. So we're going to have 55 up here at the top. And then we brought 50 down to the left, and 60 is going to be on the right. And then we have like a branch of 54 and 53, which we'll just leave for the time being. And we're just going to draw out everything else. It's 10, 5, 26, 60, 56, 70, 80. And just like before, we're going to insert that branch 54 and 53 as if we're just like inserting it into our tree for the first time. So 54 is less than 55, so we're going to go to the left of it. And then we're at node 50, so we're going to insert it to the right of 50 because 54 is greater than 50. So we have 54, and then to the left we have 53. So finally, if we draw out the balance factors of everything again, 0, 0, 0, 0, 0, this is 1, this is 0, -1, 0, -1. Height over here is 3. Height over here is 3, so that means we have 0 at our root node, and everything is balanced.
Now let's get into the extension part. So I have two questions for you guys. The first one is the code question 101, symmetric trees. So essentially the goal is to check that, the tree is symmetric, right? So like we're given this tree over here. So, when we progress down to the left and to the right, we should get the same nodes. So from 2, at this level, if we progress left and progress right, then we get the same value. In this case, example 2, we progress left, we progress right, we get the same values, great. We can't progress left, but we can progress right. And in this case, like we broke the symmetry rule, so that's why this one is false, even though, you do have the same nodes in the left and right subbranch of node number 1. So try thinking about how you would approach the solution, and I'll reveal some hints. So my approach for this is that you're going to essentially do 2 simultaneous traversals, and it's kind of like breadth first, and then what you're going to do each time you traverse level by level is that you're going to check the nodes that they exist at each point and check that the nodes have the same value. So I'm going to reveal my solution now. So here's my solution. It's not very complicated. So the first if statement is just to check that, like we are at the end of the tree. So if we reach the end of the tree, then, like we moved left and we moved right, and essentially we're at like a null, right? So not left and not right checks that, like if it's a null value where it should be a node. And if both of those are true, then that means we've reached the end of the tree, meaning that, the tree is symmetric. So one other case is that, like, if either the left or the right node that we're checking right now doesn't exist, then what that means is that, this tree is not symmetric because we have one side that has a node and the other side that doesn't have a node. So that means, like, symmetry is not conserved. And the final if statement to check over here is to check if the current value of the left and right nodes that we're comparing, if they're the same. So if they're not the same, then obviously we return false because it's not symmetric. Otherwise, we'd continue traversing to the next level. So left to the left and right to the right. So that's kind of like the outer traversal, like we're going left to the left and right to the right. So we're checking this kind of like outer side of our two sub-branches. And then the second one that we're checking at the same time is that the left right and the right left are the same. So visualizing it over here again is essentially checking, like the left right, which is 4, and the right left, which is also 4, that they're also the same. So that's my approach. And if we're thinking about the big O notation, the worst case time complexity is that, you do go through the entire tree. And if you made it through the entire tree, then that means it's symmetric, right? So that means at worst, we're going to go through every single node in the tree, meaning that we have O of n time complexity. So the second question that we have is a little trickier, and this one depends on your knowledge of in-order and post-order traversals. So this one, I won't be able to show you the best visualization for the solution, so I'll link a solution to this video. But I would really encourage you guys to review what in-order and post-order traversals are, what are they outputting, right? And then think about how you would construct a tree given just these two arrays, the in-order traversal and the post-order traversal. So some hints is that in order is in the order left subtree, roots, and then right subtree. And then post-order is in the order left subtree, right subtree, and then the root. So what that means is that the last element of our post-order traversal array is going to be the root of our tree. And what we can do from then is that we can just look at the in-order array to segment the left and right sections of the tree. And then finally, you would move backwards to the post-order array and recursively build the right tree. So at a high level, if we're just looking at example number 1 here, post-order, the last element in our array is 3, and that's the root node, right? So if we check our in-order array over here, we find element number 3, and we know that everything to the left of 3 is our left subbranch, and everything to the right is in our right subbranch. The only challenge is that we don't exactly know in which order this is, right? Because we know that 15, 20, and 7 are in the right of 3, but we don't know what order they are in without, again, looking back to the post-order one. So I'll link a video and I'll let you guys figure it out.